Today, we will be discussing the very cutting edge of direct dark matter detection and how we can penetrate the neutrino fog. What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now, today, we're going to be discussing how scientists go about hunting down hypothetical, elusive dark matter particles. Numerous strands of evidence support the idea that there is far more matter in our universe than the luminous matter we can see. The nature of galaxy rotation curves, galaxy mergers, gravitational lensing observations, the cosmic web of structure in the universe, and more, all point to the existence of a web of dark matter permeating the universe. The current consensus view is that this dark matter must consist of particles that we have, so far, been unable to observe. Direct dark matter detection experiments such as Xenon N-Ton and Panda X have scoured the parameter space looking for weakly interacting dark matter, but so far have been left empty-handed. Now, their quest to track down those elusive, hypothetical dark matter particles may have become even more difficult, as these experiments have become so sensitive that they have begun to detect solar neutrinos without seeing any hints of dark matter particles. Direct dark matter detection experiments will now need to understand and penetrate the neutrino fog if they are to fulfill their goal and track down the hidden matter in our universe. To help me dig into the present status, challenges, and exciting future of direct dark matter detection, I'm joined by a phenomenal special guest, Professor Ciaran O'Hare. Professor O'Hare is an ARC-DECRA Fellow in the Astroparticle Group at the University of Sydney and the ARC Centre of Excellence for Dark Matter Particle Physics. He's interested in dark matter, particle physics, astronomy, detector technologies and science communication, and is particularly active in efforts to extend the reach of direct dark matter detection experiments into the neutrino fog. So I couldn't hope for a better special guest to help me dig into the very cutting edge of direct dark matter detection. So, Ciaran, let's take it from the top. We have a truckload of evidence for the existence of dark matter. So we've got galaxy rotation curves, galaxy mergers, gravitational lensing observations, the cosmic web of structure in the universe, the cosmic microwave background, and more. But is there a consensus regarding what particles this mysterious dark matter might be made out of? What are we looking for here?
I would say there's certainly no consensus. Perhaps there's less and less of a consensus as time goes on, as we continue to fail to find this thing. Yeah, I mean, people fall into different camps, and there are some particular particles with particular names that people often talk about, like WIMPs and axions and primordial black holes and all of these things. I would say as sort of time has gone on, and particularly recently, everyone's sort of become a phenomenologist. We talk more about broad behaviors that dark matter could have and just trying to look for that rather than looking for some very specific candidate. I mean, it's not to say that WIMPs are not motivated from supersymmetry or axions are not motivated from solving the strong CP problem, but I think we've sort of been burned in the past, and people want to be more and more agnostic about this. I mean, ultimately, this answer is going to come experimentally. So we've got to focus on the experiments that we're able to do and make them give them as broad a capability as possible. So I think, that's the reason why consensus is sort of broadening out into just thinking about ways in which dark matter might talk to regular matter in any way imaginable. Yeah.
So instead of worrying about, you have a specific, just taking one of the slides from your talk. So rather than worrying about a particular model, supersymmetry that might give this amount of dark matter or whatever it might be, it's just more important to look and see if there are any feebly interacting particles that are hiding that we can pick up in our detector, and then we'll worry about exactly how they might have got there later. Is that kind of more of the
it's not that. I mean, that is sort of what we do these days, but it's obviously not the way you would want to go about it. It's just the way which the community started off looking for these things, coming much more from a theory-driven perspective, just didn't work out. So it's just an unfortunate result of not finding the things we really wanted to find. Yeah, so WIMPs would be an example, and it's incorrect to say that WIMPs are ruled out. I mean, there's many of the models are sort of disfavored and ruled out, but not everything.
Yeah.
So they're still interesting to look for a supersymmetric WIMP. And it's also interesting to look for any kind of particle which would behave like that. And certainly as far as the detector is concerned, it doesn't matter. It's just looking for a signal. It's not looking for something extremely specific.
I guess in the case of just kind of blue sky experimentalism, like you say, you've got the energy frontier with somewhere like the LHC where I used to work, and it's nice to have that complementarity, right, of looking for weakly interacting particles as well. So it's covering another area of that experimental space.
Yeah, I mean that's a very important aspect, and certainly if you want to actually pin down anything about a particle candidate for dark matter, you need to have multiple types of signals.
Yeah.
So for signals from space and also signals on the Earth, in some way. But as I said, we have none of those yet. So we got to find at least one thing to actually look for, just something that we can scratch the surface and try to delve deeper into. But that has not appeared yet.
Yeah. So why is detecting dark matter so difficult? Is it this idea that it must intrinsically be so weakly interacting? Is this why it's such a difficult endeavor?
Yeah, I mean, essentially, I mean, we know that because we've constrained all the possibilities, which wouldn't fall under that. I mean, if we've constrained away all of the models which would interact in even relatively strongly with regular matter, so all that's left is the stuff which is so weakly interacting that neutrinos sort of put it to shame. It's that's the situation that we're in, really.
And that's, I guess, why we have to have these huge target masses. We have to have these massive experiments that run for so long. It just makes everything more difficult.
Yeah, exactly. I mean, yeah, unfortunately, that's the situation we're in. But we've still got to try. I think this dark matter problem is important, and despite the fact that it's very challenging, we have to at least try to solve it. And it seems to be the problem in physics, which seems to be actually important for the way the universe works. I mean, there's a lot of stuff around, and we sort of owe our existence, or at least our galaxy's existence, to this stuff. And it's also a question which seems to be possible to solve experimentally by just actually finding the thing. It hasn't happened yet.
And when you talk about experimentally, what is the cutting edge? So people see these whenever we always seem to get this picture whenever there's a dark matter article in the news or in any sort of scientific outreach presentation. We always see these experiments. What is the cutting edge? How do we currently go about attempting to detect dark matter directly?
So it sort of depends on the type of dark matter you're looking for, but the types of dark matter, like for example the detector you're showing there, is really just looking for individual events happening inside the detector, where you have a detector full of atoms, and you suppose the dark matter interacts with some component of that atom, the electrons or the nucleus or the nucleons or the quarks or whatever. And when one of these dark matter particles comes in, it will have some very low probability of interacting. But if you have enough atoms and you wait for long enough, then you may see one of these collisions actually happening. And that collision will then leave some kind of energetic signal. The energy will be converted into a form that can be detected, and that's really where the field then diversifies. Like, how exactly do you extract that energy? It will depend on the medium, depend on the energy you're looking at, and the backgrounds that you have, and so on. So that's really where the details come in.
So I guess the idea is here you have a huge tank of atoms which is isolated from the outside world. You try and keep any other interaction standard model particles that we know about from getting inside. So lots of shielding under a mountain, isolated. And any particles that can still get in, like muons or maybe a neutron, you have vetoes that capture when those come in. So you try to have essentially this big bucket of super cooled isolated atoms and try to capture anything else that comes in that you don't expect above and beyond that kind of known background. Is that a fair summary?
Yeah, exactly. I mean, that you just try to get rid of everything possible. You can never get rid of everything. I mean, you can veto away certain things. If you have a detector surrounding your main detector. You can look for particles which interact in the outer detector and get rid of them if they end up in the inner detector. That's a very nice technique, and you can try to put your experiment as far underground as possible, get as much material around it as possible. That will get rid of a lot of stuff. But unfortunately, it's still not good enough. I mean, even these experiments, like the amount of effort they put into trying to get rid of their backgrounds, they still have backgrounds. So then it just comes down to modeling those backgrounds as precisely as possible, and also trying to just get as much information out in one of those events as possible. So not just, looking at how much energy it deposits in the detector, but like also looking at how much ionization it deposits, how much scintillation light it deposits, how much heat it deposits. And the more information you get, the more signals and backgrounds and different sources of particles are going to look slightly different for each other, just in terms of all of those different numbers. So that's really the state of the art is our experiments which are able to do that. They've limited their backgrounds to absurdly low levels, but then are still modeling them as well as possible and extracting every single bit of information they're able to about those events they still have.
These big target tanks, they tend to be made of huge vats of liquid xenon or liquid argon sometimes. Where on earth do they get all this xenon and argon from? I've seen some articles recently. This is just a little bit of an aside, really. I've seen some articles recently saying that they found these ultra clean. Let me see if I can find this article. Where did it go? I had it earlier, I'm sure. Where are we? Here we are. That they found these underground deposits of undisturbed argon that have essentially been around since close to when the Earth was formed. Where do they find these deposits, and why are those deposits in particular very, very useful for us in this search?
So this is argon, yeah. So these deposits of, I mean, I don't know. I guess they're just this. I mean, argon and xenon just occur naturally in the Earth's atmosphere. I mean, xenon it's I think it's a byproduct when they're distilling liquid air. They have some xenon which comes out. Argon is like one of the most abundant gases in the atmosphere. I think
it's 1% or something like that.
So this deep underground argon is kind of important for the argon experiments because there's a particular isotope of argon which is what they call cosmogenically activated. So there's a radioactive isotope which is natural in the Earth's atmosphere because it's constantly getting bombarded by cosmic rays. But if they get this deep underground argon, which has kind of been shielded for I don't know how long these deposits of argon last, like thousands of years. This underground argon has a much lower level of that particular isotope. So that's why they use this underground argon. In xenon, I mean, I think it's they have they purify the xenon and all of this stuff, but I think they don't have quite such an issue with this particular isotope that they do with argon.
Okay, so the argon, so it's not going to have as much radioactive background. It's not going to have as much of the radioactive isotope, and therefore it's going to be a lower background in your search for dark matter. That makes perfect sense.
Yeah,
excellent. So
it's the general thing that they all do. I mean, they all just try to limit all of the materials that go in underground and end up in these experiments. They need to keep them away from cosmic rays for as much time as possible. So they have to work out if some element of their detector has been shipped across sea or something, they need to know exactly how long it's been shipped because they need to figure out how much cosmogenic activation could have occurred.
It's a really nice thing that you allude to there because as you say, all of the materials that make up these vats, you're trying to isolate this vat. And if the vat itself is made of highly radioactive material or has radioactive impurities in it, those are going to provide backgrounds. There's going to be particles flying out of these and hitting atoms in what you hoped was an isolated tank. So I've even seen articles where they use these ancient Roman ingots of metal. Because they have such low radioactivity, obviously forged thousands of years ago. They've had a lot of time for the radioactive elements in them to decay away. This was, I remember 10 years or so ago, there's a little bit of a hoo-ha between the archaeologists and the dark matter scientists about this, but it just makes that point that you have to go to extreme lengths to get those backgrounds down, and that there are still backgrounds that you have to model afterwards.
Yeah, I actually saw some of these lead bricks recently.
Oh, wow.
I went to Italy for this conference where Xenon announced this result, and I was taken for a visit to the lab in Gran Sasso, and
Wow.
they have this little room where they have these little lead bars, and they still have the kind of Roman numerals on them. It's quite
Oh
quite
wow,
amazing,
that's
actually.
amazing. I think one of the I remember talking to an archaeologist about this. I think one of the stipulations of giving them was that they keep the numerals off them to so that they can keep that information later on. Or that at least they log what the numerals are. So yeah, very very cool. That's awesome. Okay, so it's clear that detecting this feebly interacting dark matter is incredibly difficult. We haven't managed to do it yet, unfortunately. Hopefully, we will eventually. And it may have gotten a little bit. Well, I say a little bit. It may have gotten a lot harder recently, with results from two very large direct dark matter detectors, Xenon N-ton and Panda X. So maybe if we talk about what these experiments saw, what did these experiments see, first of all? What are these amazing new results that have come out recently?
So this is the first signal of neutrinos interacting with nuclei, xenon nuclei in the detector. So this is something that's been known to be on the horizon for quite a while. I mean, over a decade. It's known that these experiments were going to run into the signal eventually. Actually, I mean, it's a sort of funny twist of fate. Like some of the ideas for dark matter detection were originally thought up in the context of looking for this kind of thing of
Oh
like
wow!
So
that was the
neutrinos
signal rather than the background to start with. Was
yeah.
right? Okay.
And but then it was sort of thought to be kind of slightly impractical, and then they're sort of looking for dark matter sort of took over because there were dark matter models which looked like they were with more within reach at the time. But now, I mean, this is essentially the final background that they would have. I mean, if these experiments could limit absolutely everything, somehow, let's say they went even further underground than anyone's gone before, got rid of everything, made their all their materials perfectly radio pure.
Yeah.
They would still have these neutrinos. The neutrinos are still going to get.
We just can't block whatever we do. There's no amount of shielding that we could put in place. Yeah. These neutrinos are always going to get into our quote unquote isolated chamber. So at some level, these neutrinos are going to produce an irreducible background to that dark matter search.
Yeah, exactly. Yeah, and so this is this is the final background, and they've now detected it. So the Xenon N-ton and Panda X have claimed essentially a detection. Like they've identified events which are consistent with this interpretation. These neutrinos have come from the sun. They're a particular type of neutrino which comes from the decay of boron-8 in the sun. So they're called boron-8 neutrinos. So these are some of the most energetic solar neutrinos, which is why they're sort of able to detect them.
Yeah.
And yeah, so but the problem really here is that this these events actually they're actually indistinguishable from dark matter.
Yeah.
Of a particular mass. So if you have a dark matter particle which also interacts with nuclei and it has around 6 GeV mass, it's like around six times heavier than a proton. The signals that you would get look exactly like the one they've seen. So that it's quite possible that maybe some of their events are dark matter of 6 GeV and they're just not they don't have statistics to identify them yet. I mean, that's really where this idea of the neutrino fog comes from. I mean, in particle physics, we have backgrounds all the time that we deal with, but we don't necessarily talk about having sensitivity flaws or sensitivity fogs where you can't actually experiment anymore because you're lost in the fog of the background. Yeah. The reason that this is a fog or a flaw, or however you want to brand it, is
and I know there has been some rebranding efforts which you've been involved with as well. So
yeah. So I mean, I was not I didn't come up with the term neutrino fog, but I think when I heard it for the first time, I thought, okay, that's a much better name. If you get into the details of actually what it is. The neutrino flaw sort of makes the problem sound a lot worse than it actually is. But yes, the branding is sort of has taken people seem to like it because if you want to propose a new experiment, it's good to not tell your funding agencies there's a fundamental flaw to how that's going to be. So I'm pro this rebranding myself.
So essentially, we've reached a situation where we have such high sensitivity that these WIMP interactions or some other type of dark matter particle coming in, interacting with the nucleus, that is now indistinguishable. Well, not quite indistinguishable, as we'll come on to, but they're very closely related. They look very similar in our current detection technology. That would be very difficult without huge, insane amounts of statistics to tell them apart. And this is something we can't block out. We can't keep the neutrinos out. So we now have this background of other interactions. So I think I've got this nice image that came from one of Zenon Enton's presentations, which essentially they lump these in together, these WIMPs and these neutrinos. Essentially, you're throwing them into the same bucket. So the question is, how can you distinguish between them? If you become so sensitive and you can't keep these neutrinos out, how can you distinguish between these WIMPs and these neutrinos? So this is this idea, as you said, of the neutrino floor, the neutrino fog, and essentially, I guess, where we're kind of nipping down into this sea here. Is that fair?
Yeah, so it's the sort of the shoulder, sometimes I call it, at around 6 GeV. So that's the bit that's been hit essentially by Xenon and PandaX.
This kind of downward turn here.
So the point where the limits are closest to the fog, that's the sort of the
hit, which makes sense, right? You hit the top of it first. Yeah. Okay, so we're just about touching. So I guess this is kind of a subjective question for someone who works in the field as you do. Is reaching the neutrino floor, or neutrino, let's call it neutrino fog, a good or a bad thing? Because kind of on the one end, you've got amazing, we've reached this limit that we always knew we were going to get to. We have brilliant sensitivity. We've been able to see this interaction with neutrinos and nuclei. On the other side, you've now picked up a massive new background and you haven't seen anything that you think is dark matter yet, or at least you haven't been able to distinguish it from background. So how do you see those latest results and the reaching of the neutrino fog? Is this a good thing? Know your enemy and get there and work through it, or is this a worrying thing?
It's an amazing thing. I mean, when I saw the announcement from Xenon in the talk they gave at IDM, the IDM conference, I was amazed that they'd done it so quickly. I thought it would be a few more years before they would actually put out this claim. I mean, one thing to say is it's just inevitable. I mean, the signal is there, waiting for them to get it. But that's not to say that it's just automatic that they would see it. They actually, I mean, these events, although they're predicted to be present in the detector, they're very low energy, and these collaborations had to do a lot of work in understanding the response of the detector at very low energies, the backgrounds of very low energies. Things like accidental identification of events is very important, very challenging to model. So it's an amazing achievement by both of these collaborations. That's just the first thing to say. It's also very interesting scientifically because this process, so neutrinos interacting with nuclei, has only ever been measured by one other collaboration, and that was with a neutrino source by the Coherent collaboration. They were the ones who first,
and that was much higher energy, I think, wasn't it? Because the neutrino cross section raises with energy. They haven't been able to see it down at these very low energies of solar neutrinos coming from the sun.
Yeah, so this is the first detection with Xenon, and it's the first detection of it with astrophysical neutrinos. So yeah, it's an interesting scientific result. It's particularly interesting more from the neutrino standpoint. I mean, the flux of boronate neutrinos is measured very precisely by experiments like SNO. But the cross section at that for those for those neutrinos and for Xenon has not been measured. So this constitutes the first measurement of that cross section essentially. So it's a scientifically interesting measurement. It's a amazing technological achievement that they've done. And I think it marks the beginning of this sort of new era where these Xenon experiments, these dark matter experiments that were designed to be dark matter detectors, are now actually doing interesting neutrino physics, and they're interesting neutrino experiments in their own right.
That's really interesting. Actually, I was going to ask you about that, whether you could go into the kind of neutrino. Because I've seen some kind of flag planting pieces from Zenon Enton about looking at neutrinos from supernovae and thinking about how they could actually open out into being a neutrino experiment at all. And it seems like you're saying that is a very interesting area. that we've unlocked essentially.
Yeah. I mean, absolutely. I mean, in terms of the sort of the future of this field, for example, what you're showing right now, this XLCD, this is sort of this consortium of Xenon, LZ, and Darwin. These three collaborations looking into xenon detectors. Neutrino physics is there as one of the major pieces of science that this observatory, or whatever you want to call it, will do. And it's a guaranteed thing. It's not a obviously dark matter is what motivates us all. Either primarily or as a secondary signal. Most people would put it first. But it's one that you might not see, right? It could just be that isn't what dark matter is, or dark matter lies beneath the neutrino fog or whatever. But neutrinos are actually there, and you just need to build the experiment and detect them, and then do science with them. So it's actually very important that we don't throw our hands up and say like, oh God, this is it for dark matter. Dark matter has this 6 GeV mass and is just a little bit more weakly interacting, then we're never going to see it, because I mean that is true, but that's only half the story.
Yeah, it's always nice as well to have some definite deliverables, right? When you're going to funding bodies and things. Not that you necessarily should have to have them, but it's nice to have. We've seen some of the problems with trying to get a larger collider when people are saying, oh, will you find new particles and all these kind of things. I'm going to talk about that more in another video later, but it's always nice to have these definite deliverables. In terms of the parameter space that's been covered outside of the neutrino fog, so you said we were kind of nipping on that corner now. How much of this parameter space outside, so of these reasonable masses for dark matter candidates, how much of that parameter space have we covered? Have we covered most of it down to the fog now? What's the kind of status in the field?
No, it might be easy if you go to the previous one.
This one's a little bit over, especially when it's small on your screen. It's a little bit difficult.
It's not my version of the plot. So this is a bit more clear. So everything in green has been covered essentially. LZ is leading the fields at the moment in most of the mass range. Right. Then
Xenon Enton doesn't go a little bit lower.
Yeah. So you have to do different types of analyses to get below that. You change slightly the actual observables that you pick out. But yeah, so that's it really. So that white space in between neutrino fog and the green region, that's what's left for. What's left open for discovery. If dark matter lives there, then we're in we'll be able to discover it with XLZD. So XLZD will get down basically to the edge of the fog,
right?
And then it will be lifted by the fog. And if it basically lies in that blue region,
we're going to have to deal with the fog.
Yeah.
How about the lower mass range? Is there any experiments that are going to be able to go down here? I guess when you're talking really, really low mass, maybe really low energy interactions, maybe different technologies required. I don't know if is anyone looking in that lower mass range?
There's definitely a lot of projects ongoing. They're quite far away. I mean, it's CDMS and Super CDMS. They have projections to cover quite a decent chunk of that range. There was a recent result by an experiment called NewsG, which uses a spherical, what they call a spherical proportional counter, which can identify basically individual electrons, so they can make a measure down to very, very, very low energies. And they recently had a result which it's not shown on that plot because it was more recent, but that they've carved out a little bit of that. Even lower, I mean, you have to really think about the technology to extract very, very low energy signals. So solid state experiments seem to be one of the ways to go there. But I mean, there's definitely ideas. We'll have to wait and see how they progress to see if that will actually be carved out.
You mentioned the size of some of these signals. So just to give people an idea, one of these particles, these neutrinos interacting in xenon enton, for example, releases, I think it said something like 3 scintillation photons when it hits the nucleus. So these are tiny, and releases like 5 ionization electrons. These are really, really tiny signals that these experiments have been able to pull out. So just that, to reach that level of sensitivity is an amazing achievement, even if we haven't discovered dark matter as yet. So just to give people an idea of, these are very, 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 very tiny signals that we're trying to pull out from the background. Awesome. Yes. Oh, that was one question. So I think you already mentioned this actually. So have we reached the fog faster than we thought? So I was looking when I was doing the research. I think was it Louis Strigari? I think you've done some work with him as well, kind of proposed this or mentioned this neutrino flaw 10, 15 years ago. And I think the idea was we'd
Yeah.
reach it in the next kind of couple of decades, and we're already kind of skimming it now. Do you feel like we're slightly ahead of schedule in these experiments, or are we right where we expected to be?
Yeah, I think it's fair to say, thinking, yeah, in the putting yourself in the position of somebody in like 2012, 2013, which is when the original neutrino flaw paper was written by Strigari and his collaborators. Yeah, I think probably the feeling then was that it would take a bit longer, but the thing is, these xenon experiments, especially the xenon experiments, have made unbelievable advances in limiting their background. So they've just exceeded everyone's expectations in their sensitivity. What I said previously about being surprised at how quickly the result was coming was actually more on the study that they've done. I was expecting them to want to take more data before releasing this study, but I can sort of see why they did. There's a little bit of a race because this is a
There was a
guaranteed
panda. There was a panda versus
result.
yeah.
Yeah.
I think you posted
So
on Twitter
they,
that you were surprised that Panda X got their archive paper out a little bit faster than Xenon. I think on this as well.
yeah, I've since been corrected about the flow of history. So Xenon, I think Xenon knew that the Panda X were working on something, so they were the ones who rushed rather than Panda X. But anyway, case regardless, I think they both see a consistent signal, so I think we can believe them. But yeah, there was this sort of race, and LZ is I think they're sort of hanging back and waiting to see a stronger signal before they will announce. But yeah, it's this one of these things that I think everyone kind of wanted to be first. But let's say I think we can say they drew. That's probably the most diplomatic.
On the same day is probably a draw. We'll call it a
Yeah,
draw.
yeah,
So excellent. So I guess the question becomes now, and I know you've done a lot of work in this area, and it's very much the cutting edge. What do we need to go beyond the neutrino fog, or to start searching that neutrino fog? So if dark matter does live down there, if it's incredibly weakly
yeah.
interacting, and we want to go down into the fog and look for it, starting on a higher level, what do we need? I guess it's some way to discriminate between neutrino interactions in a detector and potential dark matter interactions in a detector, right? Just on starting on the higher level, and then we'll talk about some specifics.
Yeah, yeah. I mean that's it really. I mean it all comes down to you can't get rid of them. So all you got to do is get as much information on them as possible and hope that they are distinguished from the signal you're looking for in some way. This idea of the neutrino flaw versus neutrino fog was to try and capture the idea that you can kind of brute force your way through it by just collecting
Yes, I think
huge numbers of events. So we're talking sort of thousands of events.
I've got you covered
There,
here. There we go. I've got your slide on
exactly.
this.
Yeah. So this is just a slightly more accurate just statement of the problem. I mean, if you collect enough events that you can really nail down the systematic uncertainty, or just measure very precisely the flux of neutrinos or the event rate of neutrinos, whatever your parameter is, then that's just you saying you understand your background very well.
Yeah.
So if you see any excess on top of that, then that's your signal. So this is really where the rebranding the neutrino fog, neutrino flaw to neutrino fog came from, was just to sort of identify that as a.
This is just like the Higgs, right?
Fact.
We have backgrounds for every search. We have a tiny little Higgs bump on top of a massive background. We don't call it the Higgs flaw or whatever. We just say, okay, we need to run our experiment for longer until we can get a certain sensitivity above the background. This is as long as if I have a billion background events and 1,000,000,001 signal events, okay, I'm going to have to run my experiment for a hell of a long time to see that bump come out above the background. But if I essentially, it's theoretically possible. If I keep running, and there's a slight difference between the background and the signal, I should eventually be able to tease that out. And I guess that's how you're trying to kind of restate the problem.
Yeah. So I mean that's it. It's just that sort of language is slightly unfamiliar to these kinds of experiments because they're branded as low background experiments, or in the past some of them may have been negligible background experiments or zero background experiments because they were much smaller. But yeah, so now they're just reaching into to a point where you have to use the language which should be more familiar to collider physicists. Where you got to really understand your background very well.
A messy proton-proton collider. We know all about this rubbish everywhere. So yeah. Now that makes total sense. Before we get into the specific solution, so that's a really nice statement of the case. I guess there's, depending on what dark matter is, I know there's some theoretical models where this neutrino fog might be a kind of a non-issue, right? So if dark matter is not a kind of WIMP type particle, but it's some other particle like an axion, that I guess the neutrino fog's not really an issue at all, right? Because it has different interactions with the nuclei in a detector relative to neutrinos. So depending on the type of dark matter, we don't know what it is, but if it's, say, an axion, does this issue kind of burn away?
It does, but only in the sense that those experiments are not dark matter experiments, because dark matter doesn't interact with the detector in any way. As an axion, you need a completely different type of technology. So those experiments are then purely neutrino experiments and whatever else they're able to detect. Yeah. So I mean, this whole issue is very specific to this kind of dark matter. You can draw analogous ideas to neutrino fog for any kind of dark matter model which interacts in a way that interacts in detectors which are also sensitive to neutrinos. So if the dark matter interacts with electrons, there's a neutrino fog for that. If the dark matter interacts with nuclei, but in a slightly weird way, like it mediates with the nucleus in a slightly weird way, there's also neutrino fog for that, just a slightly different neutrino fog. But there's always going at some level some neutrino fog, because these experiments are detecting dark matter and trying to detect dark matter and neutrinos at the same time.
Makes sense. So, right, we talked about trying to get rid of it depending on the type of dark matter. We talked about trying to brute force our way through the fog with extreme statistics. Let's talk about slightly more intelligent methods, which you've done a lot of work on. So, again, we're trying to distinguish between these signals, potential signals for dark matter, and these signals for neutrinos. And one way you mentioned we could be able to do this is kind of with the temporal modulation of some of these signals, and also the directionality of some of these signals. So maybe if we start on the time dependence, why would we expect a neutrino signal and a dark matter signal to have a kind of different time modulation, a different kind of temporal dependence?
So both dark matter and the neutrinos are expected to modulate over the year, but for different reasons. So as the diagram here shows, we are spinning around in the solar system, and our solar system is spinning around in the galaxy. But the dark matter halo that surrounds us, we suppose, is essentially stationary. We're flowing through it rather than co-rotating with it. So we're sort of swimming through this halo of dark matter, but the whole solar system is swimming through the dark matter halo. So if you look at our perspective on Earth, there's going to be a point in the year where we're sort of swimming into it, and then a point of the year where we're kind of swimming with the wind of dark matter. So this will lead to an annual modulation in the flux and an annual modulation in the numbers of events that you see, generally peaking in June and with a minimum in December. It's quite a small effect, but it's one which is it should be there, because it's really just coming from what we know about our dark matter halo.
So if we looked at the amount of interactions in our detector as a function of time, there could be some signals that seem to get slightly larger in June, get slightly lower in December. And if we can tease that out, adding that extra dimensionality of time, maybe we can see these time dependent signals. Is that kind of the idea there?
Yeah, exactly. Yeah. So this is expected. The dark matter event rate is expected to do this. It's a sort of percent level effect. And typically when we talk about discovering dark matter, we talk about it needing numbers of events much less than that. So this is something which you would only be able to see once you started detecting on the order of hundreds or more events. But it is a characteristic signal. It's a characteristic of the signal which the neutrinos would not exhibit. So the neutrinos would have their own annual modulation, but that's coming from the eccentricity of the Earth's orbit, the fact that we're slightly closer to the sun in January and slightly farther away in June. So the phases would be slightly different from each other, and that will be a way of teasing out a bit more information. But it's still at the sort of precision level. So it will make pushing through the neutrino fog slightly more efficient, but it's still going to be very, very slow progress if that's like the way you would go about things. Yeah.
Understood. So we can potentially, but again, it's going to require very, very high statistics, very, very long time to do this. Look at the different modulations in the year of neutrinos coming from the sun, or interactions with dark matter as we swim through that dark matter halo in our galaxy.
Yeah.
I think the smarter way, and you've done a lot of work on this, or you are doing a lot of work on this, is directional dependence. So when we look at these experiments like Xenon, they seem to say we had an interaction in our tank, we know where it was, but there's never any idea of where that particle came from. Did it come from the left? Did it come from the right? Did it come from up? Did it come from down? How can we use the direction in which particles hit our detector here on the Earth to maybe tease out a signal of dark matter? What's the idea here of directionality in direct dark matter detection?
So it's essentially the same idea that we're swimming through this dark matter halos. So as well as us having this kind of relative motion, overall there is a preferential direction where most of the dark matter will be coming from. It happens to align with the constellation of Cygnus, which is, there's nothing special about Cygnus. Cygnus just happens to be 90 degrees away from the galactic center, and we're moving, at a tangent, around a circle going around the galaxy. So that just happens to be the direction we're moving. So we expect the dark matter to come from sort of around that direction. So if we have some way of identifying the directions that the dark matter particles were coming from in a detector, that would be very good evidence that the particles were coming from Cygnus as opposed to the sun, which is typically between 60 degrees or like 120 degrees away from Cygnus on the sky. So these experiments operated more like telescopes. There would be no problem because you'd always know if your signal was coming from Cygnus or coming from the sun. So this directionality is sort of obviously the way you would want to go. The issue is, how do you actually do that in these kinds of experiments? It's definitely not. These experiments really are not telescopes. This information is not preserved in most ways of detecting dark matter. So you have to really rethink how you're actually going to do this technologically.
You've jumped onto my next question perfectly, because I was going to say yes. So at the moment, we know something hit in our detector. We know roughly where it hit. But at the moment, we don't get that direction information. And I know there's a lot of work going on. What are some of the ideas about how we could get the direction of this track? Here, it seems to be using the recoil that's created by the hypothetical incoming dark matter particle. What are the technological ideas as to how we might get this directionality information?
Yeah, so I mean, all of these signals that we're talking about are recoils, so that the dark matter bumping into something, an electron or an atom or a nucleus, and sending off the particle on its recoil. And because momentum is most of the time going to be conserved, you have the recoil is sort of roughly pointing in a similar sort of direction to the direction of the dark matter. I mean, the dark matter is gone. Once it's hit, it's leaving. So all you've got is the direction of the recoil. And most of the time, for most models and for most energies, that recoil is going to be correlated in some way with the incoming dark matter. So this is what you want to focus on. The problem is then, how do you actually get a direction of a recoiling nucleus going through a medium? And you think about the different types of mediums that you have, like liquid xenon, for example. The energies that we're talking about, like keV energies, these recoils are actually they're microscopic. They're so small that the any sort of directionality is just immediately lost by diffusion or by the charges just recombining with each other, because it's a dense medium. Solid state, there's some ways you might be able to do it, but really gas is sort of the way you would want to go, just because if you're in gas, the density of the medium is much lower, so the thing that's recoiling can actually travel much further. It can actually travel macroscopic distances, like millimeters to centimeters, depending on the density of the gas and the energy that how fast it's moving. So gas seems like the way you would go, and that's what this diagram is here. Is imagine that you've got a chamber full of gas rather than liquid, and then the actual recoils, this is a charged particle moving through a medium, so it's going to do all this ionization and stuff. It's going to liberate all these electrons, and then you could actually just physically image that. You could see it with a camera, or in the time projection chamber approach, you drift that ionization and then you image it. But yeah.
So there'd be a load of ionization along this recoil track. Those will, under an electric field, could drift up to the top. And then if you have a very fine-grained PMTs or whatever it was, photomultiplier tubes, you could kind of get a trace almost on exactly that. A trace on there would give you a kind of 2D projection of that directionality. Is that kind of the idea there?
Yeah, exactly. So you have you would just be, you'd read these this readout plane would be highly segmented. So it's full of pixels or strips or whatever, or CCDs, whatever you want to use. And then you have that finely segmented 2D plane, and then you have to recover your third dimension by just sampling it at some even interval in time, and then you look at the arrival time of the charge to build up that third dimension. So this is the approach of getting a full 3-dimensional track, even though you have to actually transport the thing from the volume to some plane. But this is quite standard technology, actually. I mean, this has been around for a long time. These time projection chambers.
How much kind of progress has been made on this? Because it seems like you said, obviously there's going to be people knew that this fog was coming up. How much R&D, how much progress has been made on potentially getting a kind of demonstrator of this up and running?
Not nearly enough. I mean, this is something you're showing a talk from 2016. I was a PhD.
Oh, this is where you've been waving your arm. Get on with it. Get on with it.
So this is a talk from when I was this is.
I hadn't. You know what? I hadn't clocked this, but that makes okay, good.
Yeah. So I mean, I've been looking at this for a long time. I mean, I'm a theorist, and I work on whatever I want. But I really.
And now we reach the fog, and everyone's going, "Oh, that's what Ciaran was talking about." Oh, right, okay.
I mean, everyone. Yeah, let me not.
No, I'm being facetious. I'm being facetious.
Yeah. So I mean, the issue is kind of people knew that this is obviously how you would tackle this problem experimentally.
Yeah.
And I think these experiments are very interesting, and they have a lot of other capabilities beyond just looking for dark matter. There is not nearly enough people working on them, and not nearly enough investment towards the people who are working on them. I collaborate with the experimentalists, and I wish all of their groups were bigger and they had more money. And I think it's amazing technology. But just to take the position that a naysayer would say is that there's a lot of downsides to this approach. The first one is this: that you're using gas. I mean, the reason liquid xenon is so good is because xenon is a huge atom, and liquid xenon is very dense. And if you have a ton of liquid xenon, that's actually quite manageable. If you have a ton of gas, there's a ridiculous amount of volume. I mean, it's just the physical size experiment you would need to just even compete with xenon, let alone push further than xenon already has. You're talking about absolutely enormous experiments. I personally don't think it's impossible. We actually have a sort of proto collaboration consortium, whatever you want to call it, called Cygnus. So the title is Cygnus. And we've put out papers sort of estimating, how big these things would need to be, how expensive they would need to be. And actually, if you compare them with experiments like Dune, for example, I mean, Dune is an absurdly large experiment, and it would be
massively over budget. It's been waiting for ages. It's coming soon. Fingers crossed.
Yeah, so I don't think these. So it's definitely not impossible. It's just it's not like an enormous community, people doing direct dark matter detection. There is limited amount of money and there's limited amount of time at our disposal. And I think probably in the intervening years since 2016 when I was giving that talk, the community has done the correct thing and to focus on liquid xenon. I think that should be said, even though I really I like this idea, and I would really like people to look into it more. But I think it's definitely the right thing to focus on the liquid xenon approach. But that being said, if the community has decided that we believe in dark matter below the neutrino fog, or we believe that neutrino fog should not be the end, this is what you have to do. Like, this is the kind of technology you need, right? So if there's a will, there's a way. So I think if people developed the R&D more, I think it would not seem as crazy as some people initially think when they come from other perspectives.
It's almost like you need some. I mean, look, I know nothing about this. It's not my field at all. It's almost like you need some sort of colloid, right? Something that has a high target mass that can then like recoil into something that's light and show the direct. It's a very, very intricate thing, and it's going to require a lot of R&D and a lot of smart people looking at it to make it work. But like you say, if they want to go below that fog, then people have got to put work into this and support it and get behind it and give it funding. And that's kind of where I wanted to talk about next. What is the future for this? Because it seems that P5 in the US, which is a kind of process where US particle physicists get behind their recommendations for the coming decade, just for people who might not be aware of this, but they're very, very supportive of dark matter experiments going forward. So I think if we go down, they are in here. I've seen them yet. Even in point 1, talking about dark side 20K, LZ, super CDMS, which you mentioned, Xenon Enton, they're very on board with supporting these experiments, super CDMS going even further. Now, this did come out before the recent neutrino fog results, but there does seem to be a lot of support for more dark matter experiments, even knowing that this boundary of the neutrino fog was coming up. So do you expect an ongoing commitment despite these results? Can we still be quite cheery in the dark matter direct detection community?
Yeah, I think so. I mean, it's great that these experiments were named. It's interesting that in the P5 report, the neutrino fog was mentioned quite a few times as sort of the, I guess, a goal for the community to reach, which is good that there is actually a limit to where you would push it, and then you would say, okay, we need to rethink our strategies. And I think so XLZD is far from a guaranteed thing. So there's a community of people interested in doing xenon. But yeah, I think that generally people are optimistic that that will go ahead and it will reach the neutrino fog. So XLZD, it has to be said, does not include the Chinese collaboration PandaX.
Yeah.
PandaX are also moving ahead much faster than anyone expected. They have so they're doing extremely well. So there's going to be still a competition. I mean, even if the Xenon and LZ in Darwin they come together, there's still going to be quite that strong competition from PandaX, which might be good actually, might be good for the field. But it's also, I know a lot of my colleagues are very worried about that. But
the reason I smile is because we have a similar situation for the energy frontier as well, where China is saying potentially they're going to build the CEPC, this new electron positron collider, which is basically Germany say, well, we're not going to pay for one of these at CERN if China's going to build one instead. We're not going to build a checker machine for China. So there are pros and cons of these kind of things in certain areas, but that's the only reason I kind of smiled at that. So, but it is good to have competition between these experiments.
Yeah, maybe it would be better to have unity rather than competition, but just because of things like the limited supply of xenon and all these sort of boring things. But anyway, maybe it will turn out to be a good thing. But yeah, I'm quite optimistic that at least the edge of the neutrino fog will be reached. I think it will be another round of decision making whether or not you want to push it forward. I would really hope there is some kind of signal between then and now that would actually help clarify the situation. I mean, the reason this is so hard is because there's just too many options for us to explore, and everyone is doing different things. So that will be the best case scenario. If that doesn't happen, then I think when we reach the neutrino fog, we're going to have to really reevaluate how we want to move forward.
So that's the kind of final question I had. So if you, Ciaran, I give you the magic wand, you've got the purse strings over the dark matter community. What does the direct detection dark matter community need to be doing going forwards, do you think? Is it finishing off that exploration of the open areas of the parameter space, and then considering whether they want to go down into the fog, and then putting funding into R&D of potential ways of doing that? What do they need to be doing to continue progress in this field, and where would you be focusing the money for that?
I try to give as unbiased an opinion as possible. I mean,
You
I
can
think
be you can be as
the gas,
biased as you like. This
well,
is your
okay,
time.
I think yeah, the gas detectors need to be, there needs to be a lot more investment in these gas experiments using the directional gas experiments, because they can do a lot of really interesting things, and if they had more money to build slightly bigger experiments, they would be able to do a lot of those interesting things, with especially with regards to neutrinos. Um, they're not going to like immediately overtake xenon, because that will take a while. But I think if the R&D continues to build up, there'll be a much smoother transition from the end of the xenon era into the beginning of the gas era, if you want to phrase it like that. But I think also that these large xenon detectors should go to their next level, like talking like 100-ton detectors scale, maybe like, well, sort of 60 to 100 tons maybe, to reach sort of like 1,000-ton-year scale exposures that would get you to the neutrino fog. And I think they should reach that scale, because that's the limit of that technology in terms of dark matter, and that should happen. I really think that should happen. I also think I would, well, this is completely changing topics, but I also really believe in axions as a dark matter candidate, and I don't think there is enough experiments looking for them, and I would like there to be many more. And all those experiments to have a lot more money than they currently do have.
So when we're talking about
anyway,
axions, this is
completely off the topic. Yeah.
This is right down in the. So if we go back to our very quickly to our diagram, I think the axions live down in this kind of lower mass.
Well, they're completely off the plot. I mean, they're orders and orders.
Yeah,
so we're talking
down here.
I sort of believe in are like kind of nano EV to like hundreds of micro EV.
Off to the left down here.
Yeah. Yeah. So it's completely different technology that you need, but they are one of the only dark matter candidates which have a very strong theoretical motivation which still stands.
Yeah.
And there's a very defined target in the parameter space that we believe they should exist in. And that's just not being explored hotly enough, I don't think. So that's also where I would dump a lot of money if I had all the money at my disposal. Yeah.
What kind of technology experiments do you need for that exploration there with axions, Ciaran?
So it really depends on the mass that you're looking for. So it's not the kind of the same idea where you just have like a big block of target material or a big tank of target material, because in the axion regime, the dark matter exhibits wave-like behavior. So you need to build an experiment which could tap into the oscillations of the waves of a particular wavelength or a particular frequency.
Like Yaxo
you
or
have
something,
to
I remember.
tailor. Sorry?
Is it Yaxo, or I remember some?
Yaxo is looking for axions coming from the sun. So so that's another important way to look for the axions. But the axions looking for the axions as dark matter, you need to really tap into that oscillations in a particular way. So you need a completely different type of experiment depending on what the wavelength of the axion is, or the frequency of the axion. So there's sort of like the classic way, which is what the ADMX experiment, for example, did, is just they have a resonant cavity, and they match the frequency of the resonant cavity to the frequency of the oscillating dark matter field. So they can excite a resonance in their device, and that would give them the ability to see things which are coupling really weakly to the photon. But if you want to go to higher masses than what ADMX is looking for, you need to look for smaller wavelengths, so that the whole experiment needs to shrink. But if you shrink the experiment, you cut its sensitivity, so that you have to be these experiments have to be extremely clever in trying to combat that. And to go lower masses than ADMX, it's a completely different type of technology as well. But yeah, so it's a very exciting world, axion experimental world.
Amazing.
Completely.
So I kind of so to summarize that, we want to, with the neutrino experiments that we've got, with the xenon experiments that we've got, we want to go down to the fog, make sure we clean off those open areas of the parameter space. We want to make sure and have a clear discussion and clear R&D for whether we want to go down into the fog. So that will include things like talking about time dependencies and dimensionality and the gas detectors that you talked about. And also we have other theoretical areas, for example, with axions that could be lower, far down in the left of this plot, where money could be be funneled as well to look at things that still have quite strong theoretical underpinnings and haven't necessarily been kind of looked at too thoroughly. So those sound like three really, really good ideas, right? And three areas of this plot which are kind of need to be ticked off, essentially.
Yeah, I mean, I think so. That pretty much summarizes my position. We'll see where the money falls, but yeah, that's my position anyway.
Awesome. Ciaran, I've really, really enjoyed this, and I've learned an awful lot as well. Thank you so much for taking the time to go through that with me, especially on a Friday evening after you've had a long week. I'm sure everyone will really, really enjoy this. Just as we finish, I'm going to make sure all of your links, the links for Cygnus as well, are down in the description. Is there anywhere where you'd suggest people could go to find out more about the state of the art in this field and keep up to date? Anywhere you'd like to funnel people to learn more?
Well, I mean, we have I don't know, we have papers on Cygnus that the people can search out if they're that way inclined. There's no Cygnus website because, as I said, it's just a group of people interested in the same idea. It's not really a formal collaboration. But if you go to my website, you can find all of the talks that I've given.
I did. That's where I began all these links
I talk at length about why the technology is so amazing and should be pursued. But yeah, so maybe that's what place to go if you want propaganda.
I'll put those links down below. So yeah, Ciaran has an absolutely brilliant web page with pretty much every talk he seems to have ever done, nicely outlined on there. So you can...
yeah, some of them I think I should get rid of, given that you've sourced talks from my PhD tests. I can't guarantee their accuracy because I was a student, but maybe I should go look at that.
And there's all kind of different levels for people on there as well. So, if you're from beginner to super advanced. So this is really, really good. Ciaran, again, thank you so much for taking the time. I've really, really enjoyed it. I'm really excited to keep up with these directionality experiments and the axion experiments as well, and see that I really hope we keep going and seeing, because it just is complementary to the high energy regime to be looking down into that fog as well. So awesome stuff. Let's stay in contact, and hopefully we'll talk again soon when dark matter is imminently discovered at one of these experiments. Hopefully, fingers crossed.
Yeah, let's hope. Yeah.
Thank you very much, Ciaran. Have a lovely weekend, and I'll talk to you again soon.
All right.
Take care, buddy. Bye now. Bye-bye. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.